Welcome to part 3 of our tutorial on op-amp basics. And this tutorial, what we're going to do is we're just going to introduce you to the concept of virtual ground, okay, which is quite an important concept, right, as I pen it down over here. Yeah, so the virtual ground concept is quite an important concept as far as understanding the basic characteristics of op-amps are as concerned. Okay, so in order to explain the concept, I'll just take help of the the open loop op-amp. Okay, so there you go, that's the op-amp. So here are its two input terminals. Okay, let's just take it as the non-inverting and inverting inputs respectively. So now if we just go forward and modify this circuit, okay, connecting two input voltage sources over here. Okay, so there we go, and having a feedback path. Okay, so you're probably wondering as to why we're adding this feedback path over here. Well, the feedback path, while being added to the op-amp, it makes it easier to operate in case of practical situations. Okay, with the open loop mode, okay, is not so very easy to work with. So for that kind of a convenience, or rather from speaking from that point of view, you'll obviously learn about what the difference is between these two modes. Okay, so just for the present moment, and just consider that this circuit is configured in order to study the op-amp in a very practical way. So that's why we're not using the open loop mode, open loop configuration of the op-amp alone. Okay, so here, as you can see, let's just apply two input voltages, let's say VA and VB, at, let's say, terminals A and B respectively. Okay, as you can see over here. So now we have other two terminals right here. At the inverting input, we have this terminal, let's say, known as terminal 2, and here at the non-inverting input, we have this terminal 1. Okay, so since we are applying input voltages right here at terminals A and B, there would be drops across the resistances R1 and R2 respectively. Okay, so we'd have a drop over here, and then the voltage at terminal 1 would be known as V1, let's say, and that at terminal 2 would be known as, let's say, V2. So here, from the output of the op-amp, would get the output voltage. And now if you just remember what we learned in the op-amp basics part 1 tutorial, that the gain, okay, the open loop gain of the op-amp, okay, just multiplies itself with the input difference voltage right here at the in between terminals 1 and 2, okay, where this input difference voltage, that's VID, is given by V1 minus V2. So the output voltage of the op-amp, okay, as we learned back in part 1 of op-amp basics tutorial, that the output voltage is basically equal to the open loop gain times the input difference voltage, that is VID, where we can write the equation, okay, as something like this. Okay, just putting the value of VID over here, that's V1 minus V2. That's great. Okay, so now we know that, or rather we came to know from our previous tutorials, that the open loop gain of the op-amp, okay, is very, very high. Okay, it's about 10 to the power 5 times more than the the input difference voltage, that is VID in this case. Okay, so here VID represents the input difference, okay, voltage. All right, so all those who have not come across this term previously, please refer to our tutorial part 1 on op-amp basics for a better understanding. Okay, so kindly keep that in mind. And now if we just go forward and look at the gain once more, you see that the gain is so immense. Okay, it's so big, or rather so large, that it can be just approximated theoretically as the open loop gain tending towards infinity. Okay, so if we just go forward and put this condition back here in, let's say, this be called equation 3. So if we just put this condition, that the open loop gain tending towards infinity, in equation 3 right over here, then we're going to obtain something like this. We're going to obtain V1 minus V2 equals to VO by AOL. Okay, so now if we just put the open loop gain of the op-amp tending towards infinity, this condition over here, then the whole thing, that's VO by AOL, would just tend towards 0. So from this we would obtain that this would imply that V1 minus V2 is approximately equal to 0. So which means that therefore we get V1 is approximately equals to V2. So this result, this result that we obtain over here is quite bizarre. So that means whenever we'd have, or rather we'd apply any input voltage at terminals A and B, we are gonna get the drops occurring across the terminals 1 and terminals 2. Okay, the voltage drops occurring at terminals 1 and 2 must be equal to each other. So this means the voltage at terminal 1, that's V1, must be approximately equal to the voltage applied at terminal 2, that's V2 in this case. So they should be equal to each other. Okay, fine. That is quite a bizarre result that we obtain from the basic equation of the op-amp, okay, all due to this extremely high open loop gain of the op-amp. Okay, so this is basically the reason why this should this condition should happen, okay, or rather this condition should present itself in front of us. So just keeping that in mind, if we just go forward and modify this circuit as such into something like this, that I'm going to show you here shortly. Okay, so there you go. If I just redraw the circuit again, okay, so there we go, and ground the non-inverting input terminal and keep the rest same. Okay, so there goes the feedback resistance, that's RF, and here's the resistance, input resistance R2, and here we apply the input voltage VB at the terminal B respectively. So now here, as we can see, the voltage, okay, at the terminal, let's say this is terminal 2 and this is basically terminal 1. So the voltage at terminal 2 being V2 and that at terminal 1 being V1, as we had seen from this equation, this circuit diagram. So if we just use the same sort of notation over here, except for the difference that we have grounded the non-inverting input terminal, so here we can see that the voltage, okay, the voltage at the non-inverting input terminal, that is V1, is equals to the ground voltage, that is 0 volts. So by using the approximation, or rather this result that we obtained over here, as you can see, V1 must be equals to V2. If we just use the result over here in this circuit, then we're going to get V1 approximately equals to V2 approximately equals to the ground voltage. So this means that V2 must be approximately equal to the ground voltage, since V1 is equal to ground voltage in this case. So therefore the voltage falling at V2 would approximately be equal to the ground voltage as such. So now we can also mathematically try and prove this thing. Okay, if we just assume the condition that the open loop gain of an op-amp is just given by the output voltage by V1 minus V2. So now V1, okay, fine. So in this case, since we're gonna put this equation as something like this, VO by the open loop gain, and now since the open loop gain can be approximated as tending towards infinity, this whole thing would tend towards 0. Okay, so there we go. So therefore we would have V1 approximately equal to V2, and now since V1 is equals to the ground voltage, then we can get V2 approximately equal to the ground voltage. So mathematically we can prove this condition this way, as I've just shown you here a little earlier over here. So basically we see that whenever the any one of the input terminals on the op-amp is grounded, okay, the same voltage gets reflected back to the other input terminal of the op-amp due to this condition that V1 must be equal to V2. And this basically occurs for the reason that the open loop gain of the op-amp is very, very large. Okay, it's as large, practically it's as large as 10 to the power 5 times the input difference voltage. So just due to this large, very large the open loop voltage gain of the op-amp, this condition, okay, so the condition over here, this condition just results, or rather just takes place. So that's why we'd have V2 equals to the ground voltage approximately in this circuit. Okay, so now this condition basically that we're seeing here is referred to as the virtual ground condition. Okay, so this condition of the ground voltage being reflected to the other input whenever one of the op-amp inputs is grounded, this condition basically is referred to as the virtual ground condition. Okay, so now if we just go forward and just state an example. Okay, let's just draw this circuit, or rather I'll just show it right over here. Let me just use the color white. So let's say we have VB, or rather let's say the output voltage from this circuit, as we're talking about, let's say the output voltage from this circuit is about 10 volts, and let's say the open loop gain of this op-amp practically is about, let's say, 20,000. Okay, so there you go. So in that case we would have basically for the overall circuit, okay, since let's say the gain of the overall circuit be represented by AV, and let's say we adjust the values of these resistances in a way that the overall gain of the circuit becomes equal to 1. So if the overall gain of the circuit is equal to 1, then we would have this input voltage, that is VB, okay, equal to 10 volts. If you're asking me why, then I would just say that since we know that the overall gain of this circuit is basically equals to the output voltage by the input voltage over here, that's VB respectively, so that's why we'll have VB equal to VO by AV. So now if you just put in the values over here, so VO is 10 volts and AV is 1, that's the overall gain of the circuit is 1, so we would have the input voltage as 10 volts respectively. So now despite this fact, now if we just did this calculation considering the overall gain to be 1. Now if we just consider only the open loop gain of the op-amp in this case, then here the input voltage being basically V1 minus V2. Okay, I'll just write it down somewhere over here. So here the input voltage being basically V1 minus V2 in this case. Okay, so if we just write down the equation that the output voltage divided by this input voltage is basically equal to the open loop gain of the op-amp, and now since over here, okay, so let's just write it down. Okay, since over here we can say that the difference between the input voltages is basically equal to let's say we're gonna have this as the output voltage divided by the overall gain. Okay, just putting in the values over here, that's 10 volts, okay, divided by 20,000. Okay, we're gonna get, okay, so this is 20,000, we're gonna get V1 minus V2 equal to 0.5 millivolts. Okay, so now since V1 over there is equals to 0, okay, so as you can see over here, V1 is equals to 0 volts as this is grounded right over here, so we're just gonna put this value of V1 over here as equals to 0, so we're gonna get V2 as minus 0.5 millivolts respectively. Just tally this output voltage. Okay, so this output voltage, as you can see, 0.5 millivolts is very minute. Okay, this is just very small. Okay, so that it can just correspond approximately equals to 0 volts. So now this 0.5 millivolt being very small or minute, as you can, whatever you want to say, so this voltage being very small in this case can just correspond or approximately to the ground voltage. Okay, so 0.5 millivolt being very small is approximately taken as equal, almost equal to the ground voltage. So over here what we are having is that we are having at the terminal V2 a practical voltage of about minus 0.5 millivolts. Okay, so which is approximately equal to the ground voltage. So now you can see here, having even an input voltage of about 10 volts, the voltage over here at the terminal, that's 2 over here, is approximately 0.5 millivolts over here, which is much small, and that is approximately equal to the ground voltage. So this is basically the condition of the virtual ground that I was just trying to cite to y'all by this means of this simple practical example. Now whenever, just remember from this that whenever any one of the input terminals of the op amp is grounded, the voltage would just reflect to the other input terminal as well. So having just said that and described the virtual ground condition by means of examples and derived results, we just come to the end of our discussion in this tutorial. Don't forget to watch our next tutorial on op amps, and till then it's just thank you for now and goodbye.